Welcome. I'm Alessandro.
I'm Tim Schaub.
And we're here to talk about pixel gymnastics with OpenLayers and Planet Labs data. So Planet Labs operates a constellation of satellites that generate Earth imagery with the goal of getting full coverage of the Earth on a daily basis. This is a lot of imagery with a very high cadence, and it lets us find things such as this. Here we have an example of imagery from Lake Manitoba. On the left, it's imagery from April 30th. On the right is May 1st, and we can see the ice thawing as spring arrives. Again, here we have another example. These are images from the village of Minamiaso in Japan. One is taken on the left here before the recent earthquakes. On the right, we have the result of the earthquakes, which is these pretty massive landslides that we were able to spot here in our imagery. So the ability to see this kind of change in our data would be great if for user to have the ability to run custom algorithms on it. And we, for example, have very simple change detection here. An example is a reservoir in California, which has a slight drought condition, as you may know. Here is a before image on the left, and on the right we have a relatively current state of affairs, and here we have the resulting change mask that is calculated with a very simple algorithm in this case. And we think that the best way to explore this kind of change for users is to do it through a browser-based tool where they have access to the imagery and they can run their custom functions on this data in real time and see what kind of results they get. So we built such a tool, which looks like this. There it goes. And here I have, it comes preloaded with a set of examples. Here we have the one we were just looking at. So this is our reservoir, and here is the change that we spotted. The way this tool works, it's an OpenLayers map that has 3 layers. We have a first base layer here that is Mapbox satellite imagery. We overlay on top of that our own imagery here that has the reduced reservoir size. And we calculate a third layer based on the 2 raster layers below it that shows us change mask over here. We can actually, in this tool, go in and see exactly what code is being run and even modify it. This is a function that gets run for every pixel in the viewport. It takes an input, an array of pixels. The first element in the array is going to be the pixel for the base layer here. The second element in the array is going to be the corresponding pixel in the other layer on top of it. And we can use these 2 pixels to generate a third layer, which allows us to show this change mask here. Now, here it is. This is very simple. We're just taking the first pixel, second pixel, calculating luminance on both of them. And if the luminance difference is within a certain threshold, we output a red pixel for our mask. If it's not within that threshold, we just output an alpha transparent pixel. We could change that up just to show you that it actually is working, hopefully. And there it goes. We got this nice P color change mask. And this is, of course, not limited to change. We have several other examples. And in fact, Tim is going to take us into a deeper dive into technology that was implemented in OpenLayers to allow us to do this.
All right. So again, we're interested in providing users with a quick way to author their own functions, in this case authoring a JavaScript function and running that on data that's been resampled and rendered for them in the browser. And the idea is that someone might tweak an algorithm a little bit and decide what kind of change is interesting to them, and then they might submit that function or those parameters to a job that would be run to create new data. Maybe this would be part of an alert service that then could alert them later when the type of change that they are interested in occurs. So with this in mind, wanting to allow people just to run really simple functions that Alessandro has been showing you in these applications, we built into OpenLayers a raster source that accepts a user-supplied function like this and any number of input sources and then runs that function over them. In this case, we get the inputs array as the argument, as you've already seen, And I just have one input source. I'm getting the R, G, B, red, green, blue values, and calculating a vegetation index just based on those visible brightness values. And then I'm returning a pixel that is green if the vegetation index is over some value, with an alpha value of about 50%, and fully transparent otherwise. So we've already seen this sort of thing running. In this case, I've got a little slider here that lets me change that threshold or the tolerance level, and I'm rerunning those operations each time I'm moving this slider. So this is a pretty simple application. There's not a whole lot going on here, but I might be upset by how slow this slider is responding to my touch. And the problem is that green function takes about 130 nanoseconds to run. So you might think that by itself is pretty quick. We don't need to worry about optimizing anything. But even in that small map there are over 461,000 pixels, and running that function on each of them blows the frame budget. So in an interactive application, you've got about 16 milliseconds to respond to user events. You don't want your re-rendering, refreshing to take more than 16 milliseconds because you start getting janky animations or boggy feeling applications. So we can't do this. We can't block the UI thread while running all these operations. It's a problem to get in the way of that event loop. You want to be responding efficiently to user events and not doing a lot of calculation that slows that responsiveness down. So the solution is to offload this work to workers. In browsers, we have web workers that we call our minions. And we can, instead of blocking the UI thread, this is sort of conceptually, you can see what's happening here. We can let that event loop continue spinning and transfer the image buffers to a worker thread. And that worker thread, the library will create for you with the function that you supply. So I'll show you some examples of this. But user supplies a function, the library creates a worker for you. Whenever a tile loads, whenever there's a reason to do new rendering, we transfer the image buffers to the worker, run the function on all the pixels. When that's done, message back to the UI thread and say, here you go, now you can, the library in this case will re-render that as a layer. So again, it's the library's responsibility. What OpenLayers does for you is create those workers. The user supplies a function, the library creates those workers, and then it handles the messaging back and forth. It transfers the buffers over to the raster sources, and then when they're done running the functions, it transfers them back to the UI thread, and then those are rendered. They can be rendered in the map. The user responsibilities then are pretty minimal. It's just to configure the raster sources, say what you want as your input sources, and then to author pure functions. And it's important to note here that these have to be pure functions that only operate on their inputs. They can't have side effects or operate on the context in which they are authored, because those functions too have to be serialized and sent over to the worker. So they're not actually running in the same context in which they're authored. So here's what it looks like when using the library. In this case, we've got, let's say, an imagery layer we want to display on the map, and that comes from some XYZ tile source. And then down on the bottom, I've created an overlay layer that has a raster source. And this is what we're talking about, or in the second half of this talk, is the raster source. This itself takes a number of input sources. And in this case, we want to use the imagery as an input source, and then we're going to run an operation on it. This is that green function that I showed you a couple slides ago. So the worker will get created with this green function. Whenever we need to re-render anything for the map, we'll get the data from the imagery source, transfer that to the worker, and run that green function on it. And that happens outside of the UI thread and doesn't get in the way of the user interaction. So you can still drag the map around, interact with other UI elements, and those operations are running in a way that don't get in the way of that. If you are running on a machine with multiple cores on your CPU, you can take advantage of this and distribute the work to multiple worker threads. So this is just another option you can supply to the raster source. You say, I want to distribute this work among 4 threads. And what the library will do then for these pixel-based operations is divide up the array buffer into 4 chunks, distribute them to 4 different workers, wait till they're all done running their functions, and then get that data back and stitch it back together and render it as a layer for you. You don't immediately want to jump to this and use as many threads as you have cores, let's say, or workers as you have cores, because there is some cost that you pay for splicing up the original array buffer, and these objects are transferable. In HTML5 we have transferable objects, so the array buffers can be transferred over and taken ownership in a new event loop without paying a copying or cloning cost. But there still is some cost when they come back of copying them and kind of stitching them back together. So if the operations you're running are very quick with respect to that time that the copying and splicing takes, it might make sense just to use a single worker. So far we've been looking at just visible RGB data and running operations on that, running little luminance calculations or other things on visible data. It's also possible to go beyond visible data. And in this case I'm showing a visible RGB tile, which we're used to seeing displayed on a map. We can also supply other sorts of data in the same tiled format for use by these operations. So in this case, Ian has named this a Brenner tile. I'm not sure where Ian is, but this is a blue red edge near infrared tile encoded as a PNG. So it's not appropriate for a display. It hasn't been contrast stretched. It doesn't look nice to show on a map, but it is useful for running operations. So this is a vegetation index that is calculated using those top of atmosphere radiance data that's outside of the visible spectrum, and it's shown over top of the visible RGB data. But this would be really useful for saying something like, I want to find areas of high chlorophyll content or look for changes of chlorophyll content at a certain level, and then make decisions about how to respond. Sorry, I meant to check what time we had here. Okay, in addition to running on radiance or reflectance data, we can also do things like run on elevation data. So I can pull in tiles where elevation data has been encoded in a PNG, and then I can create a raster source that uses that elevation data as a source and runs, let's say, a hill shading operation on it. In this case, we don't necessarily want to run a function on every single pixel. We want to have access to the whole image. So we can do things like calculate slope and aspect to determine the incidence angle for generating that shaded relief image. So you need to work on a neighborhood of pixels instead of just a single pixel at a time. And that's handled by using the operation type image. I mentioned that what that calculation does, what a shaded relief calculation does, is first calculate slope and aspect. So you could also do something like say, I want to deliver slope and aspect tiles to the client, and then they can just do the shaded relief calculation. And here's that in action. This is actually using elevation data encoded as PNGs. And then what I have in the slider here is access to the sun azimuth. So as I drag it over to my left, that's putting the sun up in the northeast corner, and then dragging to the other side, it goes to the northwest corner. So this is kind of contrived. Typically we'd say, why don't you just render the shaded relief data on the server? There's no reason to render it in the client. You might use this to do something like do topographic normalization. If you have two images that are taken at different times of day, different solar incidence angle, you can normalize the topography, normalize differences due to topography before you do a change detection on those. So the other thing I've been doing in all these examples is moving a slider and then seeing the updated operations. The way that's handled with the library, on that raster source, we have a before operations event. And you back on the UI thread get that event, and you have this kind of like user, it's your data object that you can do anything you want with it. So I can add that threshold value onto it. And in the next example, I'll show you, you can add a pixel location onto that data object, any other data that can be serialized for the workers, and then it's sent over and made available as the second argument to those worker functions that we've been looking at. So that's how things like this work, where you click on a certain area in the map. Before that operation runs, we calculate what the pixel offset is for that, send that over to the worker, run this flood fill algorithm on it, and in addition, there's this threshold that's being sent over there. So you can, in the UI, you can change the threshold, rerun those operations, and see the difference it makes there. So there's a lot more you can do with this, but we had a short talk, so we had to keep it short and sweet here. Some of the other things that I find exciting are the ability to combine vector and raster data. So everything we've been showing so far has been raster tile sources. You can also use vector data. Let's say you had a parcel map and you wanted to see in agricultural areas only what is this vegetation index. So you can run stats over your vector data by using these same operations, rendering that vector data first in an image vector source in the library. You can go the other way too. After you generate this raster data, you can do some feature extraction. You can look for edges or something and then generate features from those. Or in that flood fill or region growing example, you can also generate polygons out of that. The raster sources don't allow you to do that, but that's all possible with some little additional work. One thing that will come soon to the library as well is efficient neighborhood operations. So I was showing you two types, just pixel-based operations, running your function on one pixel at a time, or running your function on the whole image. It's pretty common that you might want to run on just like a 3x3 neighborhood. The shaded relief example I was showing, it runs on a 3x3 neighborhood to calculate slope and aspect. And we can efficiently generate that 3x3 neighborhood for you and do it in a way that you don't have to do multiple reads to the original array buffer. So that should be coming soon to the library. That's it, and maybe we have a little bit of time for questions. But okay, yeah, well, it's happy hour, right? Or it's go ahead. Yeah, okay, so the question was about how it's important for people to know, let's say, where data has come from, what sort of operations have been run on it. So it's important to be able to document the operations that have been run on data that you're working with in your agency. And in this case, we're just talking about, there's no tooling built in to the library. All of this is about sort of like real-time manipulation of data and not persisting the data, so it's just for visualization. Then if you were to, let's say, you had a service that would run that operation and generate new data based on that, then that's where you'd want to come in and ask the user for information about what the algorithm is they're using and what the nature of the change is. Yeah?
How do you handle, in the case of the hill shade, can you have workers on the hill shade use case right now? How do you handle the tiling and edge?
Yeah, good. So the question is, what do you do in the case of an image operation when you're working on a whole image? Can you have multiple workers? This image operations right now are restricted to just a single worker. So you transfer that whole array buffer to a single worker. When we add in the ability to do neighborhood operations, let's say you wanted to just do a 3x3 neighborhood, then we can go back to supporting multiple workers because we can slice up the original array buffer into these overlapping array buffers and let you run neighborhood operations efficiently on those.
Also one comment. What the hell? Awesome. Anyway, go ahead.
Yeah.
How much, in the first example, how much does the light conditions when the satellite would happen flying overhead affect the results? I'm guessing a great deal.
You mean for the change detection?
Yeah.
Yeah, I mean, those examples are in fact kind of hand-selected for the imagery that we have there, but we are working on normalizing the data in a way that it would affect it as little as possible.
Yeah, typically what you would want, these are images that are run on brightness values that have been stretched. Who knows how they correspond to physical conditions on the ground. So you typically want to run on either like top of atmosphere radiance data people talk about, or ideally some like reflectance data. So you would display one, let's say, visible set of data for the user to interact with on the map, but then you could deliver data tiles that were more, let's say, like scientifically meaningful data values. So something that had been normalized for lighting conditions, atmospheric corrections accounted for, sensor differences accounted for, and that kind of thing. You could encode in data and then run these operations on.
Awesome.
How does it handle differences between horizontal resolution and I guess they're all web Mercator time, like projection? How does it deal with any issues like that?
Yeah, so that's another limitation of this. It could be looked at as a strength in a certain way. So the question was, how do you deal with differences in horizontal resolution or distortion due to projection? These were pseudo-Mercator, web Mercator tiles we were looking at. And if you're doing area calculations, for example, it would be very inaccurate if you made the assumption that you had the same scale northern latitudes and at the equator. So yeah, that is something you have to account for if you're doing something like zonal stats or area statistics. You can also render the data in whatever projection is appropriate for your locale. You don't have to use web Mercator tiles, and you can use any projection you want and run the operations on those. When I said that it's sort of a strength, it kind of is nice to have this resampled data as a quick way to run operations on. Instead of at native resolution of the data, you're running at lower resolution resampled data. And fortunately, it's sort of how light behaves as well. If you have, when you resample in the browser, you're mixing the spectral signature from a number of pixels. That's what happens. What's happening in the browser and resampling it is similar to what would happen if you just had a lower resolution instrument in the beginning.
Are you mainly just limited to basically like what math operations JavaScript is capable of doing? Or is there anything more advanced where you might bring in some other library or something like that into the JavaScript?
Yeah, for this case, you're limited to what you can do in the language. I didn't talk at all. We haven't talked about WebGL. Some people, there's interest in running the same sort of operations in shader language on the GPU. That sort of confines you or adds different kind of constraints. Yeah, but here you've got JavaScript. You can import other libraries into those workers, but it's all running in JavaScript.
Happy hour?
Yeah.
All right.